Thanks for the introduction. I'm from ETFL here, beautiful. You can see here the logo, the library, and especially the lake, where I had the fantastic idea to take a bath 2 weeks ago, and now I have a terrible cold, so I will sometimes stop and maybe take a cough syrup. Instead, I should say got it, otherwise it doesn't register. That being said, I was asked to give this, let's say, introductory-like talk, and it's kind of an experiment. So tell me if you don't understand, if you prefer me to go fast, slow, etc. But in general, the idea is that this doesn't work. So give me a second. The idea, and now it works again. The idea is that I want to start from these 3 results, which we recently got out published. And essentially, if we have to use one-liners to describe it, one is that we want to make a measurement instrument. One is that we want to make a correction. And the other one is that we want to characterize chaos. And the objective of the talk is that you should go home understanding why we think that all these 3 apparently very different topics can actually be seen through the prism for open quantum system as something very similar occurring. So first thing first, what is an open quantum system? If it too and everybody knows it, I skip it. You let me know. We know we have quantum mechanics, and quantum mechanics has 2 rules. The first one is how does a quantum system evolve? And a quantum system evolves to the Schrödinger equation. Otherwise, better. According to a Schrödinger equation. And you have this object, which is called an Hamiltonian, and this object, which is called a wave function. Yeah, Philo. And the wave function contains the information about the quantum system, and the Hamiltonian dictates how the quantum system evolves. Up to here, very easy. Everybody knows it, right? But then the second ingredient is measurement. Is the idea that as soon as you want to know what is the state of the quantum system, you must operate with something different, something which does not obey the same rule as the Hamiltonian. And the measurement instrument can be characterized by something which is called measurement operator. And this measurement operator contains a set of objects which we call outcomes. And in its most classical formulation, you have what is called projections. So objects which squared give themselves, and morally represent the fact that this is an Hermitian operator, which is complete and orthogonal. So you measure something, you want to measure again, you obtain the same result, the von Neumann postulate of measurement. And then you describe what happens after the measurement, and you have a law to associate a probability to your state. This is fantastic. And already with these 2 apparently trivial things, you can get non-trivial physics. And it's the, let's say, birth of quantum mechanics, the Stern and Gerlach experiment. You have a beam of atoms, which is susceptible to a magnetic field. You have an inhomogeneous magnetic field. And then in classical physics, you would expect that the position of the atom at the end is random. But actually, in quantum physics, you see just 2 points. And the interpretation is that you have a set of random measurement operators, and each one projects into the eigenstate of its measurement. And so little matters what you had before. At the very end, you have the last one which measures, and the outcome of the last projection operator, just 2 values. So that is what will be today. Measurement and Hamiltonian. That being said, the type of measurements that obeys this paradigm is extremely rare. And why is that so? Because almost never measure what we claim we are measuring. We often measure something else which is entangled to the system we want to know. Let me give an example. You want to know the state of a qubit. So what you do is you send a signal in, and you collect the output of this field passing through the qubit, and you actually measure not the electromagnetic field. So the question becomes then, how do we describe this apparatus? And here we have the arrow of time, and we can think that there is an initial state, which is an entangled state of the qubit and of the photon. Sorry, a separable state of the qubit and the photon. Then this initial state gets entangled through some operation. And finally, we measure the state of the photon through a projective measurement. And here we suppose that the state which we read is associated to the measurement R of the photon, and you get this measurement apparatus. But then the idea is, if we now don't care the photon, what can we say about the measurement of the itself? The idea, is it working? Yes. It's to introduce this object, which is the measurement operator, which is the projection over the state of the photon after the measurement, multiplied by the entangling operation between the photon and the qubit. And then this object here is what we will call a generalized measurement. And now you can see that you find again the probability of measuring of some outcome, which this time will be the expectation value of the operator daga, the operator. And from this on, you can start asking yourself, okay, what are the properties of this generalized measurement itself? So again, if we discard the state of the photon, this is the state of the qubit. And we get the probability function. And we also get this relation, which is fundamental, is the resolution of the identity. It means that no matter what you do to your system, if you sum over all the possibility, something must have happened. It is impossible to lose probability, said differently. As you can see here, the sum of this in expectation give the sum of the probability. Sum of the probability must be 1. It means that after the measurement, something must have happened. So not terribly difficult idea to accept. And these guys over here, which respect this completeness relation, are often called Krauss operators. And since now we are at a conference, we need to, homage the organizers. And you see, with this Krauss, you do incredible physics. And here you see, I try to maximize the argument where we have the nice here. And is the topic of entanglement transition, of which you will learn a lot also tomorrow in Filippo's. I say it because he was in EPFL when he did it. So, of course, I root for mines. That being said, we have now our idea of what happens when we just measure once. We have our perfect measurement instrument, which reads the photon entangled with the qubit and not the qubit itself. Now we can ask, what happens in average? That is to say, if we now have our system, we want to describe the average outcome of million, 10 million, largely as many as you want, operations. And it will not be surprising to say that it will be the probability of observing the outcome times the outcome. That is the average behavior by definition. And with a little algebra, you can show that actually the formula which gets out is this one. And then you can take a different flavor in it and say that actually this weird action of something acting on the left and something acting on the right, you want to describe it as a generalized operator, as a super operator. And somehow you want to describe this sum, which now the only term which is here in R, you want to recompactify and create a measurement operator. And then there is another very important trick to say. The average behavior of a system also corresponds mathematically to what is called an unread measurement. That is to say, suppose that I measure something and you're standing next to me, but since I'm very evil, I don't know what to do. The best prediction you can make about the state of the system is its average behavior. You will tell me that with a certain probability you have something, with a second certain probability you have something else. So this idea of the average behavior is exactly the same. Oh, sorry, this is the measurement superoperator. Is exactly the same that to say that a measurement has occurred, but you have not read it. Okay? So there is a set of things you can say about the measurement superoperator. Is linear, saying that is a linear superoperator. Conserve the hermeticity, must conserve the trace, and must be completely positive. And this is what is, in a more formal language, a CPP operation, completely positive and trace preserving. But without entering details, the intuition you can have about it is that it actually represents the fact that somebody is measuring what is happening, but is not telling you. So what is that is measuring and not telling you? Nothing but the environment. Said differently. You take wrapped ions, you take the circuit of Google, and you take the IBM chip. They say we will do fantastic operations on this thing, and they do. They have incredible control of the hardware and everything. But then sometimes the result which gets out is not exactly what they want to have. And for as much as they can control each one of their operations, the main problem is that the system does not speak only to the guy who's living, but is also speaking to the system, to the environment, sorry. And the environment, which can be whatever you want, a continuous of electromagnetic mode, a continuous of phononic modes, it can be even engineered, essentially is continuously monitoring the environment without letting you know what is that it monitored. Okay? And for the sake of the talk of today, we can think that the environment will have two main effects. The first one is the lost gain of particles or energy. And the second one is the loss of information. Okay? There are many other effects, gain of particles, destruction of correlated entanglement between two very far away sites, but for the sake, let's keep it for just this. And one of the main goals that the communities of matter, open quantum system, quantum optics, quantum information, quantum computing, quantum simulation, see how many times I repeated quantum, is to control how the environment induces the loss of the quantum properties of the system or induces some quant. Okay. So now we have the rule of the game, two things, measurement and Hamiltonian. And we have understood that there is a player, the environment, which does something without telling us. That is the rule of the game, okay? There is another, if you want to be extremely precise thing, which one should add, which is the drive. The drive is, if you want, a part of the environment, which is often used to repopulate a system or to induce a continuous unbalance, bringing the system out of its thermal equilibrium. But again, for the scope of this talk, we will think that the drive is actually a part of the environment which behave in a nice way. Let me explain. In all these configurations, which are polaritonic, superconducting circuits, optomechanical, but that is true for ions, lossy positors, and condensate, and so on. What you have is that you have a kind of excitation, let's say a boson, and some form of linearity, it's non-trivial dynamics. And on top of that, you have the way in which energy is pumped within the environment, within the system. Okay? So, how does an open quantum system evolves once it does not tell you what is the outcome of the measurement? So, we have the system, and we said that the system has its Hamiltonian. And we have the environment, which a priori can induce both Hamiltonian and measurement effect, which are the only two ingredients which are allowed. And by making some reasonable hypothesis about how the density matrix evolves in time, you say that the tau is a small time, the time evolution is supposed to be linear, so you get something of this form, and this is Tau's operator decomposition of the measurement superoperator, which is the more general form of evolution. So the most simple case is one in which you have two outcomes, 0 or 1, a qubit. Two things can get out of your measurement instrument. Click or not click, nothing else. And from this, you use this idea to write a term which is proportional to tau, which is proportional to the square root of tau, because you want to get something which at most is tau. And so given the structure of the jump operator, you can make this hypothesis and you will get to something out which is at order most tau. And then you put it in an Hermitian part, which we will call Hamiltonian, and in a non-Hermitian one. So now you can ask yourself, what is this non-Hermitian part over here? And what you get, using the resolution of the identity before, you expand it. You have 1 on the left, 1 on the right. Simplify the one, and you see that the non-Hermitian part is nothing, is absolutely nothing but related to this other Krauss operator. So the thing that we get is that we will have something in which we have this click operator, and then we will have a weird action when the system doesn't click, which will be in an Hamiltonian part and some weird effect of the dynamics, soon to come later. So we put it together, we write our equation, and what we get is a unitary part of the dynamics, Limblad-Neumann equation-like, in which there is an Hermitian operator which does a commutator evolution with the density matrix, a dissipative one, which has the weird action which I pointed out before of an operator acting on the left and on the right. Now, you collect the action of rho, you divide by tau, and what you end up with is the so-called Limblad equation. Caveat, what I told you is true under 100 million approximation. However, is a very effective way to understand more or less how an environment interacts with a quantum system. Is, again, an effective representation. Works under the hypothesis that the bath is Markovian, so an excitation thrown into the bath is immediately lost. It works if the, let's say, environment has so many modes, throwing away 1, 2, 100 parts is identical. The state of the environment remains unchanged due to the presence of the system. That being said, is maybe one of the easiest models to approach the open quantum system. Okay, so now we have the Limblad master equation and we have our two interpretations. We get our quantum system and the measurement operator, which is an environment. If we read the environment as measured, we get quantum trajectories. If we don't read or we don't know what the environment has done, get the Limblad master equation. Okay? Questions up to now? I go. Yes. First of all, it's time independent, and then the linear master equation is not the most general form of the evolution of a system and environment. Like, take very strong interacting quantum system, take half of the system and call it environment, you cannot describe it. You can absolutely do it. It will not take this form. This is not, said differently, the one in which you decompose in Krauss operator is the most general form. From there to here, I made hypothesis, and this is the most general form under Born and Markov approximation. Then you have Bloch-Redfield, then you have a more complicated way of describing how an open quantum system evolves. You can have kernel, which you can have color bath, you can have ways in which you remember what happened before. You have these beautiful, let's say, diagrams in which a particle goes into the environment and comes back, etc. All very, 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 very relevant to describe certain specific instances in which the hypotheses that you are making are not true. Typically strongly correlated interaction with the environment, not break in blood master equation. Other questions? Okay. Okay. Now for, yeah. But the point is, if you want that here, we are using is the pauperity of the notation, let's say, like that we indicate expectation value in the same way if it is an expectation value on the density matrix or on the wave function. So I agree, but then let me say something. Like, of course, you don't know the single outcome behavior of an experiment, but then even classically, you can tell me, you can make some prediction without actually knowing what actually happened to the system. Take classical stochastic system, and I tell you, is a particle in a Brownian motion evolving? No, it stays in the center with the expectation value. But if I check, for example, the fluctuation, you see that they grow as square root of t. Same holds true here. Like, although you are not exactly checking the Langevin trajectory, which is telling you where is the position of the system, you know that something is happening to your system, that it's spreading despite the fact that you are not checking it. So this is the expectation value on a density matrix, which means you repeat 100 times the experiment, you measure at the end, and you tell me what is happening. This one is slightly different in the sense that if you make some hypothesis, you can know the number of excitation in your system even without measuring, because you are collecting already the outcome of your system. You see what I mean? In this case, you have always a measurement at the end, actually repeated n measurement, because you get 0 or 1. That is true. Okay. Yeah? If you want. Yeah. Okay. Now for some flavor to what does it mean, again, to measure. We take a very simple example, an optical cavity. An optical cavity, you can think of something which keeps the photon in for a certain amount of time, like 2 mirrors, and like you were kids, you go to the 2 mirrors, you see infinite copies of yourself. Same true here. And on the right side, we have what is called photon counting apparatus. The idea is that you have something, and each time photon escapes the cavity, you hear a click. And this is a legitimate way to know how many photons you have in the system. And on the right side, on the left side, what you have is a so-called homodyne photodetection apparatus, which means that the output field of your cavity is mixed with what is called a local oscillator, which is a laser. You assume it to be extremely precise, you know everything about it, no fluctuation, so it's a pure classical object. And then you actually measure the, let's say, difference between the photon in one arm. And what is important is that the object on the right is described by this Lindblad master equation, by these Krauss operator, where K can be thought as the dissipation rate. And the object on the left, this very, very weird form, where beta is the intensity of the local oscillator. And now the beautiful thing is that the dynamics of these two, written in terms of quantum trajectory, must be completely different. Is completely different, actually. You see, it's two very different equations. What is also very interesting is that both, however, describe the same Lindblad master equation, because I'm simply assessing how many particles went out of the system. So if I do the average between these two, what I get is the same Lindblad master equation in this form. Now I show you. I start from a state with 10 photons in the system. Here, each time I hear a click, the system goes down, and I see this beautiful ladder, different colors in different realization. Then I do the same with homodyne trajectories, and you see it's a continuous leakage out of the system. It does not have the same, let's say, discrete flavor. But when I do the average, I get exactly the same result, which is up to, here I did 100 trajectories up to very 10 minus 1, identical to the result of the Lindblad master equation. So this tells us two things. Like, first of all, there exist different arrangements from the same Lindblad master equation. And second, if you just know the Lindblad master equation, is a very dangerous game to guess what is the effect just one unraveling, because different unraveling can show different things. So it can be very tough to say, if you don't actually know how the environment is measuring your system, what's actually happening to you. Okay, so let's get slightly weirder. So here we pay homage to the book Exploring the Quantum by Jean-Michel Raymond and Serge Roche. So here we get what is called, another call this is the non-emission Hamiltonian, which is what happens to your system if no clicks are heard, okay? And here is instead the jump operator. So the culprit will be this guy over here. Eh? So let's start from the vacuum. Vacuum is the vacuum, remains in vacuum, nothing happens. We have not yet broken field. Now we put the state with one photon. And we see that if no jump occurs, the state with one photon remains in the state with one photon until a jump occurs, and I go down. Up to here, everything makes sense. Question, what happens if I start off from a superposition of 0 photon plus 2 photons? Who wants to answer? Somebody, you, I've seen, you've done it. It's going down the absence of jumps. And this is very weird, but you can think of it as the fact that this is a non-emission part, and the state with 2 photons decays faster than the state with 0 photon. So I prepare my state, I monitor, I see nothing, yet the system is decaying. And if I go at long enough time and I measure, I see that I have 0 particle in my system, despite nothing having come out. Okay? Now it gets weirder. What happens if a quantum jump occurs during the dynamics? Exactly. It goes down, and then a quantum jump happens, and then if I measure there, I'm sure I have 1 photon. So I repeat many times the experiment. I measure here the probability of having 2 photon is either 0 or 2 photon, and the probability of having 2 photon is going up, 0 photon is going up, and I measure more and more 0 photon, until I see 1 quantum jump, and the expected number of photons goes up, and I see more photons. So 2 very non-trivial things. First of all, the lack of quantum jumps doesn't mean that does not mean that just the Hamiltonian is happening. The lack of quantum jump means that something else is occurring. And in this case, that the state with higher photon number becomes less probable, so the state with lower photon number becomes more probable. And the second thing is that losing particle can actually increase the number of photons in your system. It is a stupendously counterintuitive effect. But if you are curious, we published an article based on this principle where you use squeezing, which is typically a quantum resource, which does the same trick, putting 0 plus 2 plus 4 plus 6. And then the fact that the number of photons increases when you lose a particle is what you use to perform error correction. More on error correction later. Okay. Let's make it even more weird. Okay. Now we have two qubits. They don't talk to each other. They just dissipate. How do they dissipate? Well, of course, they have an Hamiltonian, but they dissipate locally. So one throws away, the qubit 2 throws away to its own detector, not detective. And they dissipate collectively, which means that this weird operator is there. I initialize my system in Q1, the less dissipative. I wait enough time, and no quantum jump occurs. What happened to the system? Let's see together. Okay. Step one, let's eliminate the Hamiltonian part. We are open quantum people. We don't check Hamiltonians. Then we see that we have two things. The first one is, let's say, a non-Hermitian renormalization in the space, in the diagonal space of sigma z. And this one is a non-Hermitian coupling. So let's start from the second one. What happens if we write the physics in the basis of Bell states? Well, we see that the non-Hermitian Hamiltonian is the dissipator of the plus Bell state. Just dissipate that. If we now write our initial state as the negative plus the positive Bell states, I just told you that when there is a dissipation in this form, the more dissipative state will decay. It means is that psi minus is a dark state, and therefore it will be favored by the dynamics. So I start with one excitation in one qubit, zero excitation in the other. I let just the the collective dissipation act, no jump red, I go to a Bell state until a quantum jump eventually occurs and I go in the vacuum. Now the interesting thing is if I put back local balanced dissipation and I histogram the jump, what I see is that jumps are occurring more and more in the second qubit. So despite the fact that the two qubits are not interacting, despite the fact that I never see a jump, if I actually were to go and measure the system, I would find that the second qubit gets more and more populated. But then let's make it even weirder. Now let's introduce back the effect of the normalization. What does the normalization do? Well, it takes the state in which the first particle is excited and dumps it. And therefore, if I now write my Bell states as the superposition of these two, the state EG, where I started from first qubit excited, will decay in time. What I get is this, let me do a trotterization-like step, is this dynamics in which the collective dissipation generates entanglement, generates a Bell state. The local dissipation disentangle it and favors the state with the qubit in the other state. And then the collective dissipation acts again, and then so on and so forth. So what is happening is that despite the fact that the two qubits are not talking, despite the fact that nothing gets out of the system, despite zero click, the excitation is going from the first qubit to the second one. It's like saying, I can be in two rooms. The fact that I can go both out from both of them, but it's much more probable that I go out from one or two, makes me become localized in the other room. Not exactly a classical effect. Yes? Absolutely, absolutely. Absolutely, you can have, but then you can counterbalance for it. The idea is that you can put it back on an Hermitian coupling, which couples it back. And there is actually a very, I did not prepare the slide, but I can maybe draw it. You can actually do it in superconducting circuit, I think. Not I think, I'm sure. And you have 2 qubits, 2 reservoirs, and this reservoir, if it is driven at the right frequency, will get dissipative only for one of the 2 modes. Then, of course, the presence of the reservoir will also induce a shift. But then what you can do is you counterbalance this shift with another reservoir of opposite phase. And then you get an interference pattern between the 2. And essentially, the Hermitian coupling disappears. And you see that is only the non-Hermitian thing that gets you jump. I can go on the details on the calculation. It's kind of lengthy. But then, of course, yes, there would be, in a real experiment, there would also be the other thing. But then you can tune it and actually show that it disappears. And you can simply do the experiment around. You initialize your system in the other qubit, the less dissipative one, and you see that it never comes back. And that is a way to demonstrate that it is actually only the non-Hermitian effect that gets you to jump to the other qubit. That being said, all together, you put the system over here, you initialize one state, and you see that, boom, they swap. And the fact that if you want equivalent is non-Hermitian is that you don't see any oscillation here. In the moment in which you see no oscillation there, it means that the dynamics is purely damping and it cannot be Hermitian. To be more precise, it could still be the case that there is some Hermitian residues, but then you should, that there can be a purely damping Hamiltonian, purely damping effect, even if you have some Hamiltonian part. But then the dominant one is the dissipative one. And yeah? No, you start from 0 and 1. The state is completely disentangled. You let the environment entangle you by the fact that you are not emitting. That is weird, eh? Equivalent, yes. Yeah. Yes. 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 Absolutely. With a great difference. Here is an experiment with post-selection. So yeah, also yours is post-selection, but here you need to actually know. It's not just a change of reference. It's just that you have to add this jump operator. There are the 3 jump operators. If you remove one, this does not occur. Mm-hmm. Exactly. Yeah, absolutely. But then two things to be said. It's like saying if you were to remove the beam splitter, you would not generate entanglement. So somehow here, you need similarly this beam splitter operation in order to generate entanglement. The problem is that here, you need to have a no-click dynamics because you start from 1 particle. You don't start from 2. If you were to start from 2 particles, the thing would work identically if you were to start from 2 particles. You read the jump of the collective operator, and then the transfer occurs. Because a jump of the collective operator would put you into the Bell state, and the Bell state would then unbalance itself. That is absolutely equivalent. But then the weird thing is that here is all without jumps. It's a baroque, if you want. It's absolutely. But then the weird thing is that actually to see one event here, you need to repeat 1,000 trajectories to see one swap. So the exponential damp is there, absolutely there, but then you cannot explain it. Like this event out of 1,000, you cannot explain it. So that's why it's a post-selected dynamics. It's not relevant for anything except as an example of weird effects you get as soon as you start playing with dissipation and jump operators. Okay? Okay. That being said, there is a very poetical way copied from a very famous book. That is to say, the very fact of knowing that no dissipation occurred changes the state of the system. Is an update of the information that the reader has of the system, and this update of the information changes the state of the system. Another thing which one can do is, again, histogram the quantum jump, see that if you wait long enough, you see quantum jumps, and here again, you see the fact that you have an exponential decay of trajectories which actually arrive at long time, and therefore to see the transfer, you have to wait longer and longer. That being said, there is an article with more stuff on it, if you want to go and read it. So, last thing, and then we do pause. The third way to see this thing is the Liouvillean superoperator. So, you take an open quantum system, and you introduce this idea, again, of a superoperator, like it was the measurement operator, the object which describes the evolution of the system. You introduce the dissipator, the jump operators, and the rate at which they dissipate. Thanks to this Liouvillean, you can provide a formal solution because now this has become a linear equation, dt rho equal L rho. And you can introduce the zero of the Liouvillean as your steady state, which if the steady state is unique, you can think of, I let the system evolve long enough, the steady state. And then you can say, since it's a linear object, it admits a matrix representation, and this matrix representation can be diagonalized, and what you get is the Liouvillean spectrum. And the Liouvillean spectrum has many beautiful properties. I encourage you to go and check any books on quantum optics. And it admits a very simple interpretation. Like you get eigenvalues and the eigenoperators of the Liouvillean, and the steady state is the zero, so the one which I reach a very, very long time, which does not evolve anymore. And across the dynamics, I get all other components, which have negative real part, which means they are decaying. And if they have also an imaginary part, it means they are oscillating. So all of them compete together, and I can think of my density matrix as some sort of stair in which I have all the state. I have the steady state at the bottom and all the other states. And the open quantum dynamics is nothing but descending these stairs. And each little time it passes, you eliminate one of the stairs because it matters less and less until you are remained in the steady state. Okay? No, you have just one. This is the steady state. At the end, you have just one steady state. Lambda 1 means that it has negative real part. It means it goes down as E lambda 1t. Lambda 1 has negative real part, so it's a contraction. So just one steady state. And this will decay with a rate whose rate of decay, is lambda 1. Lambda 2 will decay faster, but it has also oscillation. So in some sense, it's much easier to see the dynamics in the other sense. From the steady state, when I go back in time, I start to see. Generically, generically, yes, but then I give you a model and I tell you how many steady states it has. I throw it in the space of models. Usually it has only one steady state. Like in the space of models which I have, you almost always find one steady state. In order to have multiple steady states, there are not super powerful theorem. There is Spoon theorem, but again, no. There are some conditions upon which you have multiple steady states which are often related to the presence of underlying symmetries to your system. I will discuss about them soon. But on a general ground, the system you consider, in reality, they tend to have only one steady state. it cannot have, a steady state cannot have an imaginary part. What you have when you have imaginary part is what is called time crystals. And the idea is that a time crystal is a permanently, forever living oscillation. These guys must always be interpreted as sums acting on the true steady state. The idea is that if you have an imaginary part and you were to have an object of trace 1, you would start oscillating, and this oscillation would reduce your trace. So you cannot be a state and have imaginary part. Or the only guy which can have a trace 1 object is this here. All the other are summed to the steady state to get physical objects. Steady states live in 0, only in 0. I can do in the blackboard maybe later, but it's super easy to demonstrate. No, you can also have infinitely many. But then this guy, if you take them, diagonalize your William, take them, and ask them, what is your trace? 0. It's always 0, except for the state which lives in 0. Because otherwise, the trace would get an imaginary part if there were to be states. Because they evolve with the imaginary part and they do not decay. So the interpretation of a time crystal is that you have here something, and then you sum all the other which are on the imaginary or negative real axis. Otherwise, they're not states. A quantum state must have trace 1. And if the trace becomes imaginary, it's not a state. Or, again, you can be in a non-trace class system, and there horrible things happen, but then I'm ignorant in mathematics to go there. Pause.
Thank you for the first talk. get started with the second part of
Okay, so now let's go to something which is which has more a many-body flavor. The idea is now to discuss a little bit phase transitions. Phase transitions are something known in condensed matter and statistical physics. And essentially, you define phases. So properties which are evidently different. So let's say order parameters which quantify their difference. And then a phase transition is the abrupt change between these two phases. So changing infinitesimally one parameter to pass from one phase to another. And you have a thermal phase transition. Today would be fantastic to have a popsicle, and you know it melts. It's nothing but a phase transition, a thermal-driven phase transition. And you have there a competition between the minimization of energy and the maximization of entropy. And the competition between these two drives a phase transition, very well explained in books of statistical physics. And then you have the quantum example, which we saw also this morning, Mott insulator to superconducting, for example. And here you have a lattice where you put bosons, photons, whatever you want. And locally they interact, and each particle can jump to its nearest neighbor. And you see that as a function of the ratio between the hopping and the interaction, you pass from a phase which is insulating, in which nothing moves, to a superfluid one, in which you can think of having an object which moves freely. And the interesting thing is that this happens at 0 temperature. And what drives this transition is the competition between non-commuting terms of the Hamiltonian. And again, this is very well explained in terms of the theory of quantum phase transition. And then to give the flavor of why what we may be saying is slightly different, I have this fantastic picture in which you think about putting a pan of water on the fire. And then you give it heat, and you ask yourself, what is the state here? Only our system is dissipative, so you now have the water which is leaking. And magically, a whole new set of questions starts appearing. Like, for example, how large is the leak? So how quickly is water going out? Time becomes immediately a feature here. How much energy is the fire giving to the water? But then our system is not only dissipative, it's also driven. So it becomes interesting to ask, how quickly are you pouring water? What is the temperature of the water you're pouring? And all this set of questions, of course here in a very classical framework, get enriched by this idea of non-commutativity of the object which you're putting inside the system. So, on a super non-specific way of seeing things, we can think of criticality in open system in 3 ways. You can have dissipative phase transitions, which can be seen, or which I will, let's say, arbitrarily define, and for the sake of simplicity, as the criticality of the steady state. You can have dissipative transitions, which are the presence of everlasting oscillation in your system. The fact that spontaneously something which was static starts oscillating, again changing one parameter. Or you can have exceptional points and dynamical criticalities. And today, just focus on the first one. So, this is absolutely a non-exhaustive list of, of examples of dissipative phase transitions. And theory, experiment, numerical, they tend to agree. So there is a lot of literature and a lot of ideas of how to characterize phase transition, properties associated to what it means, and all of them point to the idea that you have multi-stability, long relaxation times, and the idea that the Liouvillean spectrum plays a fundamental role. So to be very, 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 very precise, we say that we consider a parameter Z, and a phase transition is, we consider, we go from right to left. We have an observable, which tells us that there is another parameter. We have the steady state, which means that we have waited long enough to reach the steady state, so infinite time. Then we consider a thermodynamic limit of the system so that we can have non-analyticity emerging. Then we consider the derivative as a function of the critical parameter, of the parameter going to the critical point. And if this is divergent, then we have a phase transition. A jump, first order, an elbow, second order. That's not the end of the story because, again, here there is a thermodynamic limit. It's stupendously difficult to reach the thermodynamic limit in open quantum system. Exactly, there are techniques to reach thermodynamic limit or to guess what are the behavior of thermodynamic limits. And sometimes it's very difficult to also check just the steady state as there are, around the dissipative phase transition, critical slowing down phenomena occur. So you get this very, very, very long dynamics, hysteresis, instability. So, that being said, there is another point to specify, which is often not so thought about. And is that when you are thinking about phase transition in a Hermitian system, you have this picture of exchanging states, which often can be adopted to describe phase transition. You have a state A and a state B, and when they cross, the minimum of energy exchange. So you have a phase transition in the sense that the property of A are very different from the property of B, and you get this exchange of state, which is called phase transition. You can say I do the same with the Liouvillean. I have my spectrum, I have the steady state, I have the first excited state, and I say that the phase transition is nothing but the exchange of these two states. There is, however, a problem. The fact that the trace of the first eigenvalue, which is non-zero, is 0. So this is not physical state. So this picture that two things are exchanging is not valid, because otherwise you would end up with a state which has 0 trace. So it's not a physical state. And instead of speaking of, the other problem is that in Liouvillean theory you cannot have a positive eigenvalue, so you cannot actually have an exchange of eigenvalues. So the idea is that more or less, instead of speaking of, let's say, level exchanging, one can speak of level touching, one can speak of closure of gaps, and there is some caveat when discussing it. But then without entering in the details, this is a very old work I did when I was in Paris with Cristiano, and more or less much of the mathematics to describe this problem is laid out in the book by Tosio Kato. And the idea is that you make some request about the steady state remaining at symmetric, so trace class operators and a well-defined positive, etc. Hermitian. So, what do you predict out of it? That you get first order transition, and you have this, which we call point-like closure of the gap, while you scale towards the thermodynamic limit, which is something which gets a minimum, and this minimum goes down and down and down. You get phase coexistence at the critical point, and you get metastable states around the critical point, what you would call hysteresis. And this is a first order transition. Very, very closely related to phase transition in thermal system. And to give a little bit more a flavor to this thing, one interesting feature, let's say, of this driven dissipative system is that while normally phase transition emerge in a thermodynamic limit of infinitely many components, in bosonic system, it's sufficient to consider one mode to see some signature of phase transition. And the idea is the following, that now the thermodynamic limit can be reached by considering many particles in the same system. I will give you a justification, but for the moment, believe me that this has been seen, let's say, in some example. And the example we will focus on today is that of the Kerrison. So we have drives, dissipation. This is what we call one photon drive, exchange photon at the time, two photon drive, two photon at the time, dissipation of photon 1 by 1 and 2 by 2. Okay? We will not consider all of them together, but then this is the general model. So, before I forget, tomorrow's where is Alex? Alex's talk tomorrow, it will be a lot about finite component transition, so I don't go into many details today. So, why do I claim that there is a thermodynamic limit in a single resonator? I will do something very crude, don't criticize me on that. Consider a lattice of resonators, n resonators. They are coupled, they're hopping between them, and each one of them dissipates, each one of them has nonlinearity. And then I pass in the K space, in the momentum space of this resonator. And then I get my equation of motion in K space. Then I can say something, that is to say, I consider just the K equals 0 mode. And if I just consider the K equals 0 mode, what I see is that I get a rescaling of my parameters according to the number of sites I considered initially. That is to say, if I consider just the uniform mode of a lattice of resonator, I can think that a single resonator in which I rescale the parameter captures the same physics. Of course, you cannot capture non-local objects. Of course, you cannot describe fluctuation above the K0 mode, but still is a guideline to understand why one speaks about finite component transition. Absolutely, if it is two photon dissipation. One photon dissipation, the idea is that here we are speaking about average quantities. So you can think that emitting from one site or emitting from two sites is like emitting the collective mode, symmetric and antisymmetric, if the rate is identical. The mathematical trick, but it works. Like the Limblad dissipator of A1 plus, sorry, take dissipator cavity 1, dissipator cavity 2, and eject a photon. Same rate, K dissipator A1 plus K dissipator A2 is equivalent to K dissipator A1 plus A2 over square root of 2 plus K dissipator A1 minus A2 over square root of 2. But then I can say, I pump the 0 mode, the uniform mode, because all the drives are coherent, and all the other mode will be empty. So if all they are empty, I just neglect the presence of the other dissipators. Everything is in the vacuum. I'm in a tensor product state. I just remain with the K equals 0 mode. It's an approximation. It's not true, what I'm saying. Like, I assume that only the K equals 0 mode is populated, and then it follows that. Absolutely will not be the case. Absolutely. Absolutely. Yes. No, but I'm not claiming that the two physics are the same. I'm claiming that you can see the thermodynamic limit in a single cavity. This. Yeah, but still you can see. Yeah, they are not the same. But then no, it's not absolutely, again, absolutely not true. But then my point is that you can, is an argument to say why you can see the thermodynamic limit in a single cavity. Which if suppose you take a Hubbard model, you cannot see the thermodynamic limit in a single cavity. It's a cavity. The point here is that you have the drives which allow you to reach the infinite, the border of the Hilbert space. That's different. But then yes, absolutely. Like, don't take this as, I can now study physics of correlated dissipative system by studying one cavity. No. Okay, sorry. So, Kerr resonator. Detuning, interaction, one photon drive, and dissipation. Now, single cavity, we have our scaling, and then we ask ourselves, what happened? You have two terms, detuning and interaction. And these two can compete, because one can increase the energy, and the other one can decrease the energy. Again, here we are in a frame rotating at the pump frequency. So it's not really that you are decreasing the energy, not that you have negative energy photons. But the energy of the photon is negative with respect to the pump. Okay? So you lose energy from the pump, and you gain energy from the interaction. And simultaneously, you have two other terms which can compete, which is drive, which populates the cavity, and dissipation, which empties it. So you get this idea of the competition between these things. And if you now go and study by numerically diagonalizing the system, again, rescaling the parameter according to the scaling, etc., what you see is that you have a first order transition as you increase the drive, from a vacuum phase to a very populated one. And if you now go and check what is the Liouvillean gap, is the slowest time scale, you see a plot very similar to the one I plotted you earlier, in which you see that there is a critical point, and this critical point is going down, and this represents the closure of the gap. Now, picture here what happens. You have this guy that bloop immediately goes to the other side. Of course, it's a finite size effect, so here there are actually points, but then as you scale toward the thermodynamic limit, you observe the actual first order transition. And then again, there are a set of beautiful experiments in which you see this physics playing a role and the emergence of a first order transition. Now, is what I'm discussing. Thank you for the question. Excellent question. Convergence of great minds. So let's go to discuss second order. Let me also introduce the idea of symmetries. Symmetries are not stupendously necessary for second order, but is easier to discuss second order phase transition with spontaneous symmetry. So let's take this idea of photon exchange 2 by 2 this time and the tuning. We are here in a Hamiltonian setting, and the idea that A goes to minus A leaves the Hamiltonian unchanged is what we would call a symmetry. The symmetry can be seen as the fact that you have an operator which is parity, and parity commutes with Hamiltonian. Everybody's happy. And now we can, the presence of this symmetry means that our Hamiltonian block diagonalized. We have a set of even state and odd state. And you can see that symmetry means conserved quantity, meaning that even states speak only to even state, odd states speak only to odd state, and the quantity which is conserved is actually the object which commutes, parity. Parity commutes, parity is conserved. I start from even, I exchange photon 2 by 2, I remain even. Okay? Let's go to open. So now we have the same object for Hamiltonian, but we add one photon dissipation. The photons are emitted one at a time. Okay? If I send A into minus A, the Liouvillean remains unchanged. Do you agree? Here I put minus 1, minus 1 makes 1. This is U1 invariant, this is U1 invariant, so Z2 is preserved. Everybody's happy. Okay. Does it mean that I conserve the number of particles or parity? No. Because now I start from 0, I go to 2, I lose one photon, I go to 1. So the idea is that symmetry does not entail anymore the conservation of a quantity. Okay? So what is the meaning of symmetries in open system? So, to be very precise, we need to introduce two concepts. What someone calls weak and strong symmetries. There are many definitions, I stick to this one. Weak symmetry means that you have a super operator which commutes with the Liouvillean. Okay? And the picture you can have in mind is that now, instead of having the Hamiltonian, which is decomposed into two blocks, is the Liouvillean, which is separated into blocks. And these two blocks does not mean that you will not meet even and odd state, but you will not generate any coherence between even and odd state. Said differently, you start from even, you will either go to even coherently, so you can have a quantum superposition of even state, but then sometimes you will jump to odd states. And there is an incoherent process which jumps from even to odd, is the loss of one photon. So the density matrix we write as a probability times an even matrix plus another probability times an odd matrix, and never coherence between the two. That is the idea. At steady state, always at steady state. More generally, you can write Zn symmetry, you can write translational symmetry, you can write whatever you want. And for example, for Zn symmetry, meaning that you exchange n photon at the time, for example, you will get that your steady state and your eigenstate are constrained by the presence of a symmetry. So the take-home message is that still you have a constraining of your dynamics, not as strong as in the Hamiltonian case. If you want something as strong as in the Hamiltonian case, what you introduce is a strong symmetry. Okay? And the strong symmetry is more complicated because now you ask that there is an operator which simultaneously commute with all the jump operator of your system and with the Hamiltonian. Said differently, if you take the system, which, for example, as before, has 2 photon drive, and you put 2 photon dissipation, now you still dissipate, but then even remains even, odd remains odd. Okay? What does it mean is that now you have, instead of 1, let's say, quantum number, 2 quantum numbers, one which represent, if you want, the states, and one which represent the coherences. And these 2 quantum numbers tell you what happens to the dynamics of your system. So it's a more constrained dynamics. And in this case, you restore this idea that symmetry has conserved quantity. And this is one of the few cases where you have multiple steady states, for sure. If you have a strong symmetry and does a conserved quantity, then you have multiple steady states. And then, if you want, there is this weird diagram of what means to have a strong symmetry. It means that if you have a strong symmetry, you have a conserved quantity. But if you have a conserved quantity, you are not guaranteed to have a strong symmetry. If you have a strong symmetry, you are sure to have something which commutes with the Liouvillean, but if you commute with the Liouvillean, you are not sure to have a strong symmetry. So somehow you have broken other theorems. Okay? Yes? Yeah, these are the density matrices. Yeah. Sorry. Like the idea is, yeah, these are. No, they're not independent steady state. You have just one steady state, which is the superposition, even, and odd state. Thanks for the question, sorry. Okay. Now, second order dissipate phase transition with spontaneous symmetry breaking. So what you get is now that the symmetry of the system imposes a structure of the steady state, and the symmetry breaking can be seen as the fact that eigenstates which do not respect the symmetry, the original symmetry of the system, close, become 0, 2. They still trace 0 object. And then by summing them to your state, you obtain something which is not an eigenstate of the symmetry, but still is a steady state. And we take our 2-photon Kerr resonator this time, which has weak Z2 symmetry, because again, A can go into minus A and nothing changes. And then you see here, there is the emergence of a second order phase transition. And if you go and check what is the Liouvillean gap, it goes down, 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 meaning that a state which is symmetry broken will never go back to the other state. And if I now plot it, here is the critical point, it squeezes and you get these 2 states. And the time it requires for one of these 2 states to go to the other state diverges. Meaning that you have broken the Z2 symmetry, which is in a phase space representation means that Z2 means that you have a center symmetry. You have the central point of your phase space, and anything must be reflected. You have broken that symmetry. On a time scale, which becomes 10 to the 9, 10 to the 10, the typical time scale of the system. Preview. So, we have collaborated with Professor Scarlino in EPFL, who has a fantastic superconducting circuit. And I know maybe you can't see anything. Yeah? Okay, no. First, quite frankly, no, we did not look into. There are people looking into that. I'm not one of them. But then the whole question of dynamical critical exponent, it's probably something which my feeling would be you find a way to break the idea of dynamical critical exponent. Like because another thing you can do, of which I'm sure, is that you can take a system which has a second order dissipative phase transition with spontaneous symmetry breaking, cook up by hand some weird dissipative current, and eliminate the spontaneous symmetry breaking, keeping the second order transition. That is not true for first order. First order have always, so essentially you can build up some weird, the easiest thing you can think is take a laser, okay, Laser is a dissipative phase transition which breaks you one, because you develop something which has a phase, kick some detuning in your system, meaning that the output field of your laser, you scramble it. Is no more, what you read is no more U1 symmetry breaking, because you lose the phase immediately, yet the system has a second order transition. So again, maybe it's much less, like you can do terrible things to your open system and it still remains a Limrod master equation. Okay. Not yet guaranteed, but usually yes. You can have multiple steady state on top of the symmetry. But then, yeah, but again, there are arguments often given for why there is a unique steady state. But then it's super difficult to generate multiple steady states, and it's terrifyingly difficult to generate more than two. So, yeah. The best example I know is two steady states for a very little time, which is Schrödinger cat states, more later. Yeah. 3-photon drive, 4-photon drive. Yeah. Okay, no, you need multi-photon drive. There is a fantastic experiment by Per Delsing, I think, or people north, and they have done 3-photon drive, 4-photon drive in a single cavity, and you see 4, 5, 6 coherent state. Now the point is that if you want to stabilize states in which the quantum coherences between the coherent blob are there, then you need n photon dissipation. So if you want to stabilize, not exactly true, but then in a first approximation true, if you want to stabilize a cat state more later, you need 2 photon dissipation to overcome 1 photon dissipation, or linearity to be much larger than 1 photon loss. That's one of the reasons why they do it in this copper. They put things inside copper so that it's extremely non-dissipative. Okay, but anyhow, flux line. This is a resonator. This is a feed line. Essentially, what you're doing is you have this circuit over here, in which you drive the squid at double frequency. This does down conversion because it's a nonlinear element. This down conversion drives the system 2 photons at the time. And then here, in which no signal is passing, you collect your signal and you do heterodyne detection of your signal. Okay? And what you observe is this as a function of detuning and of pump power. You see the emergence of this very abrupt jump on one side and a smoother jump on the other side. And then you can do the tomography. You actually don't see the number, me neither. There should be number here. This is taken on the left. This is taken at the critical point where you see the state is squeezing more and more and more and more. This is taken in the bright phase where you have 2 lobes. And this is taken exactly at the critical point of the first order transition, where you see the presence of multi-stability and jumps between the vacuum phase and the high population phase. Yes? Finite size effect makes it that you will actually jump from alpha to minus alpha. So you are not actually broken. You never jump. But then I can show you soon the thermodynamic limit in the sense that, give me a second. So here is actually cuts taken here. And then when you reapply the rescaling of the thermodynamic limit, here you have some finite size effect, but then you see all the curves collapse one onto the other. And you see here the second order transition and here the first order. For the second order transition, you can extrapolate. This is all experimental data. You can extrapolate the Liouvillean gap. And to give you a scale, here is in second. So it means that the resonator has 10 megahertz of dissipation. It means that it jumps, let's say, roughly every millisecond. A photon is emitted. And here the state is, I know you can't read, I hope you have a better resolution. This means 10 seconds. It means that the lifetime of the alpha state is 10 seconds. So you are orders of magnitude. Sorry, microsecond I meant, not millisecond. So you are 7 orders of magnitude longer lifetime of the alpha with respect to the lifetime of a single photon. So to all extent is infinitely long-lived. Then you have the first order dissipative phase transition. And again, you can extrapolate the gap. Here you don't see the other region. We are still taking the data. But then what you will see is this something goes up and closes the Liouvillean gap. Yes? No, go. The shoulder. Ah, sorry. Here is the total emitted signal. So in yeah, in this case, yes. Yeah. Yes, but here also is a very semi-classical model in the sense that if you go here, the critical exponent are the mean field one. Yeah, absolutely. This is a mean field like physics. What is interesting is the again to quote Julia, the finite size effect of it, like the fact that you manage to capture the presence of finite size effect, and then something more which maybe I'm discussing. Other questions? Yes. Go. Worst case we don't finish. I'm happier like that. Through here. Photons of the resonator go in the feed line and then get read by one photon dissipation. Yes, is absolutely one photon dissipation. To get to photon dissipation, you would have to engineer much more the system, and you would have actually to get photons emitted through here, to the flux line. To photon dissipation, are you familiar with the parcel effect? Parcel effect. Okay, to photon dissipation is nothing but the parcel effect of an element which is twice the frequency. Parcel effect. Parcel effect is you have a very dissipative element next to your parcel, guy long time ago, put an atom in a cavity. And then he asked itself, what happens to the cavity lifetime? And the cavity lifetime went down, or vice versa, nobody remembers, or up, or, okay. And the idea is that put a dissipative element next to an object which is non-dissipative induces dissipation in the object. Now the idea is, if you have next to you something which is at twice your frequency, you cannot dissipate because there is too much energy difference. What can happen, however, if you have a nonlinear element which mediates the interaction, is that you send 2 quanta of energy to your dissipative element, and that gets dissipated. But dissipating 2 quanta of energy is like 2 photon dissipation. So like we're spannometric, eh? Okay? Yeah, the classical superposition of 2 states, alpha and minus alpha. This is absolutely non-trivial, is how long it takes for the state alpha to jump to minus alpha, and how does it do it? Because classically, you would say that the state alpha is forever lived. Quantum mechanically, as soon as you have you have 2 sources of noise. The one given by the measurement, or by dissipation itself, and the one given by quantum mechanics. And both of them compete into giving you a jump from alpha to minus alpha. And the other interesting thing is that, I don't know, you cannot read the numbers, but here 2.5, here is 2.4 in the tuning with respect to the central frequency of the cavity. The idea is that here, at the critical point, you have actually 2 time scales which are separated. Sometimes you jump from the vacuum to the state with many photons, and some other times you jump from the state with many photons to the other by breaking phase. So you have this competition of these 2 phenomena, and part of the work was to find a theoretical way to disentangle them and be able to extrapolate them separately. And yes, like the idea is that quantum effects are in the rate of jump, and there is some quantumness also here in the spontaneous symmetry breaking, which can be used for quantum information. This is not exactly the best resonator because it's, again, too dissipative and too much dephasing, but is a precursor of something which can be done. Maybe I have time to talk about later, but then we will see. Okay. So that's not the end of the story. Like what we discussed today is critical slowing down and finite component. But then also with Filippo, we did the phase transition in lattice systems. Then there are no standard effects, the one I told you about earlier of breaking the symmetry, and second order phase transition with or without symmetry breaking. This is exactly the case of the laser, in which you can destroy symmetry breaking by adding dissipative current, etc. Now, let me run through an application in 20 seconds. So, We have seen that we have this resonator. Now we want to use it for quantum sensing. Why is that so? The idea is you have a measurement instrument, you have a quantum system, and you want to read what is the state of the quantum system. Now, how do you do it? Quantum mechanically, what you do is you put in the middle a ket state, or something which is kind of large and very entangled. And then by coupling your system to the ket, and then measuring the ket, you get an enhanced response. This is the principle of quantum sensing. You make the sensor better by coupling your actual system to an intermediate step, which is very quantum, very entangled. So how do you actually measure a qubit normally? Say, you have your cavity, you couple your cavity to the qubit, and then you drive your cavity, and you detect the output field of the cavity. And the idea is that you have a James coming like Hamiltonian. So qubit and cavity exchange one quantum, you drive it. And then if you are dispersive enough, you have what is called a dispersive coupling. The easiest way to understand this is the following. If the qubit is in the ground state, a photon can jump between the qubit and the cavity, virtually, if they are detuned enough. But if the qubit is in the excited state, no matter how much they are detuning, this transition is prevented, and therefore there is a lift in energy. So if you write the Hamiltonian in this dispersive regime, you get that the state of the qubit shifts the energy of the cavity. But then, you know this is an almost linear cavity, you delta omega this detuning, you get a coherent state in your cavity according to the amount of drive you have, and then you go and see. Like this would be the cavity part without the qubit. If the qubit is down, it's here. If the qubit is up, it's on the other side. You check the phase, you get a response. What are the limitations? Measurement must be slow in some sense, because you want that the Lorentz state cavity does not cover the shift induced by the qubit. And you need that the detuning is very, very, very large, so that you are not actually driving the qubit through the cavity. These two limitations somehow poses the constraint of this system. So essentially what I'm saying is that you are sitting on a Lorentzian, and no matter what you do, you are still sitting on a Lorentzian, so you cannot modify the underlying shape of the Lorentzian. Okay? But now it would be much better if we had something in which, if the qubit is up, we have bright emission. If the qubit is down, you have no emission. Okay? But then the thing which we are looking for is something which is very related to what I just told you. You want something that, aside from requirement, is critical. So somehow changing very little one parameter must produce very different effect. And as we just saw, there are two types of criticality, first and second order. We know of, and then we know how to make them in the lab. So the idea is, if we use one photon drive, we rescale, we have our first order transition, and we can think about a protocol. We initialize our system, we couple it to the qubit, we wait delta t, and then we measure. And then it would be fantastic, because here, changing very little, we have a very, 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 very large response of the system. But then there is a problem. And this large response comes at the price of time. That is to say, there is a critical slowing down. So before you see that actually the system has jumped, a long time has passed. And therefore, the actual amount of information you get out at each dt is very small. And also, the qubit can emit during that time, get an excitation from somewhere else. So actually, it's not good to do measurement across a first order transition in this sense. There are other protocols, but not this one. But then what about the second order? Of course, we know the two-photon drive has also first order, but then it has also second order one. The question is, can we use the second order transition to do metrology? And the idea is that of all the points you want to sit where the squeezing is maximal. So somehow here you have classical-like regime, which are described either by the vacuum, which is a classical state, or two coherent states, which are again very classical. The point where you want to sit is where you are extremely squeezed. The point where you're extremely squeezed is quantum. So here, there you can have a quantum enhancement of your measurement due to the fact that you are squeezed below vacuum. Okay? So again, we rewrite, in this case, the two-photon drive, but the shift in the tuning remains the same. And then you want to have finite size criticality. You don't want to have infinitely many photons. Like you cannot put the sun next to a qubit and pretend that the qubit remains a qubit. Like there is a limited amount of photons you want in. And then you write your limit master equation. And then the idea is the following. Here is the state without the qubit. Now, by changing an epsilon, the state of the qubit, you see you get two very different states. One which is less squeezed and one which is a coherent state. Again, for the sake of simplicity, this approximation here is what I told you about. But then, of course, there are many other effects, the parcel effect that we discussed earlier. There can be photon-induced tunneling between the qubit and the cavity. And there can be indirect drag of the cavity. Like that is to say, the two photon drive here can get in resonance with weird processes here, which drive the qubit. So, we check. First, is the measurement feasible and precise? You can define the probability of an error in a qubit. Literally is the distinguishability between two density matrices. And then you say that theoretical calculation tells you that you can reach extremely high distinguishability. But then on this plot, you need to put the qubit degradation. That is to say, this eta parameter tells you how weakly you are destroying your qubit. And you see that you find some very good 10 minus 4, 10 minus 5 precision for your qubit. Then the question is which quantity you need to measure. And you see the difference here is qubit up versus qubit down. And here is a quadrature of the field. So how do you measure quadrature of fields? With a homodyne measurement. So the point is what you do is you measure the quadrature of your field. The probability of having an error is the overlap between the two distributions when the qubit is up and when the qubit is down. You go and check it, you do simulation, and you see that despite not being the ideal error, you still get an error of below 1%. And the other thing is that the minimum of the homodyne detection corresponds to the minima here in the ideal error. Yes? It doesn't matter because shifting your said differently, shifting your qubit, the squeeze state means that you add more photon to your cavity, and adding more photon to the cavity breaks again the qubit. This is the line where the qubit gets broken. So it's as much photon as you can put in the system before the qubit breaks. Said differently, shifting the state in the qubit would add more photon, in the cavity would add more photon and thus break the qubit. So it would mean that you have actually to move the curve, put less photon, and then ask yourself again the question, is it the maximal precision? Yes, absolutely. But then quantum Fisher information, we looked at it for magnetometry purposes. Here, distinguishing between two states is discrimination rather than quantum Fisher information that you look at. Here, you want to really distinguish between up and down. So it's a discrete variable. Okay? So, precise and feasible. So, rapid and projective. Again, we do the same protocol. Prepare, couple, measure. And in this case, again, we sit at the critical point. And what you can see is that, and this is fundamental of distributed phase transition, not all observable have critical slowing down despite the spontaneous symmetry. And here you can see that the number of photons, for example, reaches rapidly the steady state, despite the fact that alpha to minus alpha takes a lot of time. So if you initialize well and in the vacuum, you see that immediately you get a signal out. You don't need to wait a long time. Projective. What do you do to check if the measurement is projective? You initialize along sigma x, and you want to measure sigma z. So here we initialize along sigma z. And in the time more or less in which the system reaches the steady state, you see the qubit has been projected up or down. So this is a projective measurement. And half of the time you go up, half of the time you go down. Here is 6 trajectory, and 3 goes up, 3 go down. Then, of course, if you want the experiment, 4 goes up, 2 go down, but then in average they go up and down. And then there is the unwanted action of the cavity in your system. And what you can see is that here, if you start from a qubit, let's say, which is up, sometimes through the cavity you will induce partial effect and loss. But then you need to repeat 10,000 times this experiment before you see once that there is the degradation. So the degradation induced by the cavity has been chosen so that you are in the same order of magnitude of degradation. The precision was 10 minus 3. Here, 1 every 10 minus every 10 to the 4 trajectory gets destroyed due to the presence of the Hamiltonian. The other thing which is interesting to see is that there is this minimal effect on the Hamiltonian. This is the second order coupling which you get. You don't only get parcel effect, but you also get a lump shift, and this lump shift reflects in the Hamiltonian. All to say, yes, we have a measurement instrument, blah, 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 and a perspective is that we are now investigating the time correlation of fluctuation, which is terrifyingly complicated to study on pen and paper. So what we did was to give it to a machine learning algorithm and then understand if the machine manages to extrapolate information through the noise of single trajectory. And actually, yes, you get very precise region. Here, white means it's stupendously precise as a function of both measurement time and frequency of measurement. Then all this to come. Since I'm very late, do you want me to flash one argument or I stop it here? Tell me. Back. So, either critical Schrödinger cat qubit or quantum chaos. Raise hand. Who wants critical cat qubit? Everybody needs to vote. That is the other condition. 2, 4, 6, 8, 10, 12. Oh no, guys, but okay, 2, 4, 6. Chaos. Chaos. Here we had the beautiful picture of the cat, like, look, all of it, beautiful cats. Okay, transient steady state quantum chaos. So, story goes, we were here last year, and Camille Aron gave a fantastic talk on quantum chaos. And then to me, which was not clear is we have a phenomenon which is contractive. The Liouvillean is a contractive semigroup. So you have something, you initialize your state, it goes to the steady state, always. How do, like, can we define chaos then only as a transient state, as something which is transient towards the steady state? Can we do something else? And then we tried to answer this. It came out actually 24th of May, like 2 weeks ago. So it's basically. So, classical chaos, you have an initial state, you have a sensitivity to an initial condition, it's expressed through the Lyapunov exponent, and you get these beautiful pictures in every article. For example, this is the Lorentz attractor, fantastically beautiful. Quantum chaos. In quantum mechanics, the idea of dependence on the initial condition is slightly more broken. Like I give you a system which suppose I have a discrete spectrum. The idea of chaos suddenly doesn't make so much sense. But then it was Wigner and other people a long time ago, which had the intuition that chaos can be seen as an emergent phenomenon. And then there is a deep connection between the spectrum of your Hamiltonian system and the spectrum of random matrices. And in particular, there is a quantity, which is the distribution of spacing, which is an indication of chaos. Let me explain what I mean. If you have an integrable system, it means that there is an underlying set of integral of motion, which makes your system block diagonalizable. But if you have a system which is block diagonalizable, you can have what is called avoided level crossing. Get two systems separated, they don't speak to each other, they can have the same energy. There is nothing which prevents it. Then you have what is called level clustering. But if you don't have these underlying symmetries, then it means that your system cannot have two identical energy, because you will have a level repulsion. Like you take a qubit, you try to make the energy identical, you get a level repulsion. And therefore, instead of having level clustering, you will have level repulsion. So this idea of chaos in terms of underlying symmetry of the system is what gives you this, let's say, level repulsion distribution and Wigner-Dyson distribution in a Hamiltonian system versus Poissonian. And it's related to this idea of random matrix theory. From there, people said, okay, what can we say about open quantum? And the idea is that you can generalize this idea of level statistics also to Liouvilleans. And then, in particular, by Prosen was introduced this idea of the next to nearest neighbor complex breaking ratio. And you can see that there is this appearance of, let's say, this is the Liouvillean spectrum, the spectrum of the operator. And you get, of this, sorry, Z parameter, and then you get these holes which open in transitioning from integrable to chaotic system. Very nice. But all of these, again, is on the spectrum of the Liouvillean. It means that you are decaying towards the steady state, and once you are in the steady state, it makes no sense to define chaos in this way. Because the steady state is one eigenvalue, and one eigenvalue does not have any statistics. So the first question which we also asked is the following. Take our fantastic model now that we know by heart. And then this guy, if you put enough energy in it, will have a statistic which goes as the number of photons squared. And therefore, if I am to take the infinite dimensional space of just one single oscillator, I have my low-lying space, and then something which goes as n squared when I put enough photons. And this is integrable. So if you take a bosonic system, it's driven. I have no symmetry underlying. I need to take the entirety of spectrum. Where do I put my cutoff? Because I have always something that at high enough energy is integrable and is separable. Because it's simply the statistics of equispaced levels at very high energy. It's separable. If I put enough particle and I give you a chain of resonator, these don't speak to each other because I have so many particles that no, I mean really, I give you a single cavity with n photons in it, is integrable. And then I give you a set of them, and then the question is, oh, then I give you where do I cut the spectral statistics? If there is a set of separate, like you can rewrite your state as a set of separable cavities at high energy, like there is a set which grows larger than anything else, which is of integrable state at high enough energy. You can see it like in this model. And then the question becomes, how do I distinguish what are the relevant state of my system? And then, as I told you, the second point is that there is no distinction between transit and steady state. Like I go down my stair, I arrive here, nothing happens here if I take this picture. And let me say there is a criterion which has been proposed, which is this entanglement Hamiltonian, the log of raw steady state, which is a very good idea. We found some cases in which it seems not to work very well. So this is another justification for why we want to check this. So to give you the idea, what we want to do is, if we now go back to our old quantum trajectories, we see that, for example, here we are changing a drive in two coupled resonators. And you see there is clearly an idea of chaos here. Like, you know, that doesn't seem very regular as dynamics, no? So the question is, can we take this idea that there is something, you know, not very regular that we see and make it as rigorous as the spectral statistics? And we did something remarkably easy in my mind. So first you take a quantum trajectory, single quantum trajectory. From a quantum trajectory, build the associated density matrix. Now this density matrix can be decomposed in its Liouvillean features. And then you check what are the coefficients that you activate. And then if you put a cutoff there, and if these coefficients are activated, you do the spectral statistics on these states. Repeat many times to get an important sampling of quantum trajectory. And then you have now a criterion which automatically selects only a portion of the bosonic space and can define steady state chaos, because you wait long enough, your average has reached the steady state, but this is still a pure state which selects things. And then you take an array of resonator. In this case, the array is long 2. You do the spectral statistically of the density matrix built up by quantum trajectories. Is not exactly like, because the entanglement is done, on the log of the raw steady state. Here you're doing something non-linear at each trajectory. You're building up the statistic of each trajectory. It's very much more related to entanglement transition. You're doing something on the single quantum trajectory. So much so that we see. And yeah. Yes? No. The criterion is you select the eigenvalues. You have now, you have your density matrix, rho. Rho is made of quantum trajectories, okay? These quantum trajectories, you pick them out one by one. And then you ask yourself, which spectral components does this quantum trajectory activate? Said differently, if I were to give you a state which I followed up to the steady state, let's say up to very, very, very long time, is a state, is a wave function, and I stop telling you what is its dynamics. You need now to know all the eigenvalues which this trajectory has activated, all the this one. You decompose. This gets you the coefficient, and then you take the coefficient which are larger than I don't know, 10 minus 3, 10 minus 4. It's like a cutoff in a bosonic space. Yes? Yes, but you can always decompose a pure state in terms of infinity of your Liouvillean spectrum. Ah, sorry, is the Liouvillean eigenvalues. Eigenoperators. You are decomposing your single quantum trajectory on the Liouvillean eigenoperators. And this decomposition allows you to discuss what is, for a single trajectory, the spectrum which you activate. Absolutely. Absolutely, yes. Because in this way, you can have the notion of something which continues to evolve even at the steady state. Because, What do you mean? Yes? By tracing out what? But then this would be entanglement phase transition. This would be much more related to entanglement. Yeah. Yeah, these C are trace of rho times the left eigenvectors, eigenoperators of the Liouvillean. Huh? Is linear in this row. But then this row, you take the absolute value of this Cj, which is the nonlinear part, and you select this guy. Here you say you are selecting, like you get your spectrum, like I show you here, much clearer. You get the spectrum. This is the spectrum of your system. And then you ask, which values is the trajectory switching on? Which values gets, I repeat one trajectory and I say, I now decompose it in the basis of the Liouvillean eigenoperators. Which one of those is switched on? And then I repeat, and then I repeat 100 times. And then at a certain point, this quantity converges. And then I say, these are the eigenvalues which I actually need to describe my dynamics. How are they distributed? Do they have a regular distribution, and then my system is integrable? Or do they have a chaotic one? And then you, in this way, you can define chaos even if you are at the steady state. Excellent question. For system which does not admit an underlying symmetry, what we observe in our case is that it does not depend on the unraveling. For system which admit an underlying symmetry, yes, this will depend on the unraveling because again, it depends on the type of trajectory you're doing. Different unraveling will explore different parts of the spectrum. Absolutely. That is absolutely known. Yeah. Yes, but first, I don't know how they scale. Also, for a practical purpose, like we managed to study 3 cavities, but then I expect them also to scale exponentially, because exponential is large, like is a large exponential the space of Liouvillean states, So I expect them to scale as well exponentially. Like the number of states needs to scale exponentially. But then this is not a problem because you simply need to reconstruct what is there. Yeah. So let me. No, like the point. No. The Limblad would give you the same result. But then the point is that let me tell you here. You see this white line marks the region where the Limblad finds chaos. I give you the Limblad, I take a cutoff, let me say arbitrarily, and then I ask itself, do I find chaos in the spectrum? And the answer is yes. Yeah, I take the whole spectrum and I say, do you find chaos? Yes. Instead, this region red over here is where I let the system evolve to its steady state. And then I pick up these trajectories and I interrogate it, do you see chaos? And the point is that, said differently, here you see, at the very end, you have 5 possible processes which describe your steady state. If I take a trajectory at the steady state, there are 5 possible decay times. So despite the dynamics being maybe not integrable, as I will show it to you, this steady state is integrable. I find this is not steady state. This is not integrable. Here, if you do the statistics, it is not integrable. So we have example of non-integrable transient, integrable steady state. Yeah, we need to.
After 5, so
yeah.
To wrap up. The last question.
Yes. In this case, it doesn't make sense because the steady state is just one eigenvalue. So how can you do the statistics on one eigenvalue? So you see my point. If you were to look at the eigenvalues of rho, in this case, you can, in this specific case, so you do log rho, and you do this entanglement, you would find chaoticity in this case. The problem is that, for example, already in this case, you find chaoticity, but then is the steady state, according to us, is not chaotic because it's just one state. Like you are decaying into the vacuum and you tell me I'm chaotic. Not exactly. Okay, but then wrapping up, 20 seconds. I skip. No, this is like, come on, because the number of eigenvalues was over 9,000. Easter egg, sorry. I skip experiment, I skip the lack of BGS. This is when you go to lattice, don't care, conclusions. So, Open Quantum, I hope I convinced you, is interesting even beyond studying Open Quantum itself. Distributed phase transition are a very cool phenomenon. I hope some of you will study it. Schrödinger cat, you have not seen it, so, but then we have dissipative chaos, and again, what to me is interesting is this perspective of looking in the same way in which you look at entanglement transition as some phenomenon which emerges once you look at single trajectory. The same to me may be true also when you start looking at dynamical phenomena such as dissipative chaos. With that, I have concluded. Sorry for being long. Thank you for your attention.